A very warm welcome to all of you to our second session of the second day, that is control and planning. We have three exciting presentations lined up for this session. So one reminder that please ask your questions in the questions tab of the live discussion tab. There are also some polls which you can take part in, and we'll try to answer those polls at the end of the session. So first up is Jordan Palacios, software engineer at PAL Robotics. So he'll be introducing ROS-I control, what's new, and some practical demonstration. So Jordan, if you can share your screen and if your mic is on, the floor is yours.
Hello everyone. Hash already did the presentation, so we can jump right into the ROS-I control project that we are going to be talking about today. Now. All right, so let's do a quick overview. So first, we are going to be talking about what is ROS control. That is the predecessor of the ROS-I control project that we worked in the last year. Then we're going to talk about the goals and the design for ROS-I control. Then we'll show you a quick demo with three of the most popular ROS-I controllers using the Tiago robot. And finally, we'll talk about a bit of the community. So ROS control, it's a framework that offers the capability to implement and manage robot controllers. These controllers make use of the standard ROS APIs or ROS interfaces. So any ROS application can make use of them to operate a robot. Good examples are Move It for commanding, for example, a robotic arm, or the ROS navigation stack for commanding wheels. ROS control also gives you the tools so you can implement your own hardware abstraction layer. So with this layer, you can expose the information from sensors and actuators. You also have a transmission interface that lets you convert the data coming from the actuator layer to the joint layer. And controllers ultimately use the joint layer. And so another focus that was strongly put into this project is real-time performance. All the code is real-time safe. And this was done because the idea is that in the end, ROS control was intended for state-of-the-art robotic platforms. So those kind of platforms usually have hard real-time requirements. You can also dynamically load, stop, and start controllers, even if ROS control is already running. Once again, these operations are real-time safe. Also, since the controllers work with agnostic hardware interfaces, you can share them between different robots with a minimal configuration setup. ROS control also gives you hardware resource management. So you cannot have more than one controller working with the same command interface at the same time to avoid clashing. And finally, it is seamless integrated in Gazebo. So the same controllers that you use to operate a robot can be used to command a simulated robot under Gazebo. So now let's move on to the goals for ROS-I control, which is the project that we've been working in the last year. So it is the idea is that it will be the spiritual successor for the original ROS control. And we wanted to offer the same kind of features while at the same time addressing some of its limitations that became clear after years of use in the original project. This time around, we also wanted to have the project be heavily community focused, just as the original ROS control. So the first thing that we did is that we contacted Ben Magyar, who is the current ROS control maintainer, and also an ex-colleague from PAL Robotics. So he helped us set up a discourse to ask the community for their feedback. And we were glad because the response was very positive. People show a lot of interest, and they wanted to see this in ROS-I. And they also expressed their opinions on what they would wanted to see different, or what kind of new features should the ROS-I control give. So after that, we created a ROS-I work group. and we meet every 2 weeks since the beginning of the year. And the idea where there we discuss possible new features, maybe bugs, what have you working on. It's a friendly discussion. And the good thing is even people from third-party projects come around and see how maybe they could make use of ROS control to the benefit of all the community. So now let's talk a bit about some new features of ROS2 control. Well, as we said, with time we spotted some of the limitations of the original code. We feel that, well, with the benefit of hindsight, we could say that some of the parts of the original ROS2 control code base feel maybe a bit over-engineered. Perhaps one or two hierarchies out there we could make out with. So we wanted to put the focus on having a simpler code base, because what happened originally is that since the code was so complex, it made it hard for newcomers to start contributing right away. So this time around, we'll try to keep things simple. And I think it has already paid off, because a lot of people have already done some contributions to ROS2 control. We also have a component-based actuator sensors and systems. And we'll talk a bit more about this in the next slide. And in ROS2 control, the hardware interfaces can be dynamically defined. So in the first ROS control, the problem was that the hardware interfaces were always position, velocity, and effort. And you were obligated to offer these three, even if your actuator didn't support one of them. This was not ideal, but even worse was the fact that you cannot add new interfaces. So if you have an actuator with a temperature sensor in the motor and you wanted to expose that, you didn't have the option. Or maybe the value of an absolute encoder, or perhaps a different kind of a command interface like torque. The only way to do that is to add new interfaces by modifying the whole code with huge refactorings that would also break API. So that's what's not convenient at all. This time around, the interfaces are defined using the simple string, so they can be whatever you want. And it has already proven to work very well with even supporting the original ROS controllers that it had already been implemented in this iteration. We also have a new vector that is called the resource manager for better handling the hardware interface claiming, the hardware resources, whereas before it was just a simple check at the start or the stop time of the controllers. And finally, two new features that are the controller changing and independent controller loop rates, which coincidentally this came as a request in the ROS discourse. So now I'd like to talk a bit about the design. I will switch to an image so we can zoom a bit, since maybe the letter is a bit small. So you would have your robotic platform that usually has some sensors and actuators, and you want to able to recommend this. So you have the components, sensor, system, and actuator. So a sensor accesses the data from a single sensor, of course. An actuator does the same for an actuator, but at the same time also allows you to command them. And then we have the system. A system is a component that is able to access or command several sensors and actuators. So you would use a system whenever you have like a set of actuators and sensors that are coupled between each other, that you cannot really command them individually. This is usually the use case for commercial robotic solutions. For example, a KUKA arm, where the way in which the manufacturer lets you control the arm is always by moving the whole thing, or rather you have to provide a command for all the joints. You cannot move them individually. So to each component, you can ask it to export its interfaces. So you get state interfaces that are just data, it's read-only, and command interface. That's the one that lets you change the state. So this would make sense for actuators. And all these elements reside inside the resource manager. So the resource manager checks the configuration from somewhere, usually the URDF, loads the specified components, and then for each component, it asks to export the interfaces. And then this interface lives inside the resource manager and can be used by the controllers. We also have the transmission tool that this time is kind of optional, but that the system and the actuator can use to, again, translate data from an actuator level to a joint level. And then we have the second actor, that is the controller manager. Once again, the controller manager checks the configuration from somewhere, for example, the URDF, and in there loads the specified controllers, the code A, B, C. So when the controllers are loaded, they ask the interfaces that they wish to access. And the control manager relays this petition to the resource manager. So if there is some kind of clash between these interfaces, the error would be spotted at this point. Otherwise, these interfaces are granted. And when the controllers are unloaded or stopped, and the resource is returned to the resource manager. So this is basic scope of the current design. Let's go back to the presentation. And now I'll show you a quick demo with the 3 of the more used controllers using a Tiago robot from PAL Robotics. So this robot is still working under ROS-I, but what we have done is that the robot controls, the motor control side has been migrated to ROS-II. So we have kind of a hybrid system. And here, so we have the motor control node, or the rather robot control node, that has inside the hardware abstraction layer as a system, and then the ROS control running at the same time. So what we do is that once the node is started, the load controller service is offered by the controller manager, and this service allows you to load the controller. So in our case, the joint state controller, which is of type joint state controller. And then with another system that's called the switch controller, you can start and stop any number of controllers at the same time. So we do that. We start the ROS, the joint state controller, and we check in this topic the current state of the robot. So in here we have the list of all the available joints and the position, velocity, and effort state of these joints. So this is a very simple controller that lets you know the state of the robot. In fact, the name controller is a bit misleading. So let's jump to the second demo, which is the diff drive controller. So this controller reads a command, a velocity command that is given in an angular velocity and a rotation from a topic, and converts that to velocity, to a velocity command that is given 2 wheels. In our case, 2 wheels, because Tiago robot has 2 wheels. So once again, we load a mobile-based. Sorry about that. Jump. Okay. Okay. So we once again we load a controller called the mobile-based controller that is of type diff drive controller, and we start it using the switch controller service. So now we'll check that the topic for the command is actually empty, so we are not receiving commands yet. And we'll switch. We are in another tab. We'll start a ROS bridge that will let us expose this topic in a ROS-I environment. So we publish there a command velocity. In this case, with a linear and angular rotation. So we see that the robot is already moving. It started to rotate on place. And we can check that in the ROS-II environment, this topic is being published too. So this way we have communication between the 2 environments. And for the last demo, we'll show the joint trajectory controller. This controller is used to send in a set of points or of a trajectory to 1 or more joints at the same time. So once again, we start the robot control node. We load the controller, and we start it. And this controller gives you an action, so you can send the goal as the trajectory goal. So it's already there. So we start once again the ROS bridge, and then we have another instance of the bridge that is specifically for exposing this action. So the idea is that from the ROS-I environment, we'll start the action client, and we'll send the trajectory there from there. So what the idea is that since not all applications of the robot has been migrating yet, with this we can still use application from ROS-I to command the robot that it size in ROS2. So here I have pasted a pre-prepared motion of the arm. We'll move the arm to what we call an offer position. And after that, we paste another motion to send the arm back to its original position and send the goal. And that's it. So the idea is that with this hybrid system, we can still use the original Move It and the original ROS navigation stack to operate a robot that's been already started to be migrated to ROS2. Let's go back to the presentation. So now let's move on a bit on the community. So I mentioned that a lot of people show up to the call of ROS2 control, and I wanted to give my thanks to them, especially to these four: Ben Smagliar, Carsten Ness, Dennis Toggle, and Victor Lopez, for the whole amount of work that they've been doing in the last year. A heavy push has been done in the last 2 months in order to have a stable and version of ROS control released in Foxy. So thank you, everyone. And here, well, the repositories were created back in 2017, but real work on the ROS2 control project by us started in the last year. So I want to show you the huge amount of the difference in work rates. And finally, if you want to get involved, I'll leave you here some addresses for the working group in case you want to join. Or you can also check the agenda to see what we've been up to in the last couple of weeks. And some resources. Well, you were already mentioning these two repositories that contains most of the source code. You also have the roadmap with the list of the features that we've been working on and the upcoming stuff. And finally, the ROS2 control demo repositories with some examples of fully deployments for ROS2 control with the Edamir robot. Thank you very much.
Thanks a lot, Jordan, for an amazing presentation. You already have quite a few questions lined up, but we'll try to take it once the session is over. Right. Thanks a lot.
Thank you.
Next up is Henning Kaiser from Picnic. He's a roboticist there. So he will be presenting Move It for ROS2, real-time support and industry adaptation.
Hi everyone, really nice speaking here. I'm going to quickly share the screen. I hope this runs up nicely with the last talk, because we're really excited about the upcoming ROS2 control releases, and we are really looking forward to use it with Move It as well. Is my screen visible?
Yes.
All right. Okay, let's get started. Okay, I'm going to share the latest updates and Move It for ROS2. I'm going to start with a quick roadmap status update, highlight the Milestone real-time support, talk about the features Move It servo and the upcoming hyper planning architecture, and about what's our plans for the future releases and any kinds of application and demos that we are working on right now. So currently we're working on 3 milestones. Well, basically the first milestone is already done. The straight port to ROS2 is considered completed. Our current focus is on milestone 2, real-time support, which includes a couple objectives that I will walk you through really quick. And milestone 3, fully leverage ROS2, which is more like a long-term milestone for enabling all the ROS2 features and Move It, and really using all of the things that we think are really useful in ROS2, like lifecycle management of ROS nodes and component nodes, improved messaging, and so on. So for milestone 1, we have a total progress rate of 94%. There are 4 packages not ported yet, but those are not ported because there are like major blockers which require like re-implementation of critical parts. For instance, the Move It setup assistant needs a major redesign because of the new launch system in ROS2. The perception stack had some blockers, but it will be finished the next weeks. and bullet and thread job are both experimental features that weren't completed at the time where we were porting where we were doing the ROS-II migration. There are 3 really nice demos that you can try on with Move It 2. Move Group, Move It CPP, and Move It Server are 3 different ways on how to interact with Move It and how to write your applications. So here is a quick demonstration. You can basically do everything with a Move Group node in ROS-II as you were used to in ROS-I as well, using the motion planning panel, dragging around that interactive marker and running motion plans. Of course, you can use the same interface in your C++ application as well. The Move It CPP demo is a CPP node that is pretty much a demonstration of how to run a full motion planning pipeline and do collision checking with a collision object. So it pretty much shows you how to use all of the Move It components in a single class application. The real-time support milestone. We are currently really wrapping up most of the objectives in this list. There's reactive closed-loop control to sensor input, the separate global and local planner architecture, hybrid planning, the zero memory copy integration to controllers. This is still a little bit pending, but we are really focusing on that once ROS-II control has consolidated more. And the integration of built industrial motion. It's a motion planner for industrial trajectories. So the reactive closed loop control feature is pretty much implemented by the new post tracking library that we added to Move It Server for ROS-I a while ago. This is currently being ported to ROS-II and allows you to run 60F PID controller motions for Cartesian motions for any kind of input that you want to actually run it with. So if you have a closed loop control application that should react to a visual input, like a visual post that you want to track, then you can directly feed that information into that interface and Servo will handle the rest for you. Servo will internally run distance-based collision checking so that you don't run into self-collisions or object collisions in the scene. And this also supports dynamic scene updates. We are already using this one for a couple of projects quite successfully, and we are really excited about that new capability. So please feel free to check this out and let us know about any problems that you might run into with it. Then there's the new hybrid planning architecture that we're working on right now. There's an intern student at Picnic right now, Sebastian Jahr from Karlsruhe Institute of Technology, fully working on that and until the end of January 2021. And until then, we are planning to have that architecture completed in a way where you can start playing with it, exchange the planners and try to run different applications with it. The current status is that research is completed. There is an early architecture design draft, and we are right now working on the actual plan implementation. So we hope that we have the first motions executed by the end of this year. I will talk more about the hybrid planning feature in the hybrid planning section. ROS-II controllers or zero memory copy integration of ROS controllers. This was a really early milestone that we made when we didn't really know yet how exactly the realization of this will look like. At this point, I think we can be really optimistic that the zero memory copy integration will be realized really soon, and that we will also be able to directly use that in different architectures, like for instance, the hybrid planning architecture. So yeah, not going into details too much, but we are considering using ROS-II controllers as local planners as well for hybrid planning, and also to focus our efforts on better integration of ROS controllers in the Move It architecture in general, like switching controllers and running mixed control applications, like switching between trajectory and online control. This is a really important step for us as well. And yeah, this we will focus our efforts on that in the next months. The integration of the Pulse Industrial Motion Planner. This has been done for ROS-I. We have already synced this to Move It 2, and we just need to port the planner plugins, which shouldn't be too difficult actually. And then we can also check this one off. So one of the most exciting features this year that we're added to Move It 2 is Move It Servo. We had a Google Summer of Code student, Adam Pettinger, working on that feature, and we pretty much did a really great job of refactoring JogArm, which was the first version of this online control interface, and clean it up in a way that it really works nicely with ROS-II as well. This includes component nodes and inter-process communication to really use the best of what ROS-II has to offer. Here's a little example. You see Adam Pettinger running a teleop operation on the left side, controlling a robot's end-effector with pretty much with a sense, and running different manipulation tasks with it. Internally, Servo will allow running position or velocity streaming using an inverse Jacobian. So it's purely based on processing real-time Cartesian commands. It will check for joint limits, collisions, singularities, and it is really useful if you just want to run any kind of motions online. The update rate of Move It Servo is usable for running online because the collision checking will allow you to react on any upcoming changes with a really high frequency, like 50 Hertz here. One problem with that is that if you run multiple motions in a really complicated scene, then you might still skip some updates. And ROS-II comes in really handy here because you can make sure that your scene updates are coming in time and that they are always up to date. So we can make sure that the state of the scene is always valid and up to date. The update rate is still a bit too low for really making sure that you can have a stable and robust real-time application. So we are also looking into increasing that collision checking update rate. But this, I think I will talk more about this problem of online collision checking and robustness in the hybrid planning future, because it's really related to the local planning problem that we are looking into right now. Here you see another example of using different input frames, using the post tracking API, and handling like sloppy sensor input as well. All right. Skipping to hybrid planning. You've seen that Move It Servo is only running Cartesian input. It doesn't do any planning. It doesn't do any intelligent steering around collision objects. It will only slow it down or stop the motion in advance to not run into collisions. Hybrid planning is a way to realize online motion planning to directly interact with a scene that changes while you move. So in Move, the current approach is a sense plan act approach. So you have a scene, you plan a motion, and then you execute the motion. You assume that the scene doesn't change while you move. As you see on the right, this doesn't work well if the scene changes. You run into collisions if a collision object is invalidating the trajectory. So this is a really common problem, and there are some approaches to solve this problem with replanning, but this was always really limited by the performance of your architecture. Another approach that at solving this is the local reactive control. Similar to servo, you would have a solver that iteratively tries to find new control directives that steer around collisions using maybe a local distance field, some optimizing solver that can run really fast, but doesn't have a lot of information about the global problem. The biggest weakness here is that it might get stuck in local minima, as you see in the example of the right. The robot stops and then isn't able to run around it, and only after removing the object, the robot can steer to the goal state. So the idea in the hybrid planning architecture is to pretty much marry both planning approaches, global and local planning, to allow solving both problems at the same time. An example for hybrid planning is, or a goal for hybrid planning is to execute adaptive and reactive motion using global and local planning architecture. The difference between adaptive and reactive motions is simply that adaptive motions react to a local problem. They adapt to an uneven surface, for instance, when drawing on a chalkboard. And a reactive motion reacts to a global problem, like, for instance, steering around new collision objects in the scene. I'm gonna skip this slide because I'm running out of time a little bit. So you see on the right example, a continuous motion planning approach that marries both planning approaches. The global problem, the global planner will replan the global trajectory, while the local planner is following the trajectory that the global planner provides and still keeps away from collisions locally. Here you see the current architecture of that planning approach. It's based on 3 components. You have a hybrid planning manager that maintains the planning logic, handles planning requests. That planning manager initializes and interacts with 2 planning components, the global and the local planner, which both have access to the planning scene and maintain their own planning problems. When the global planner publishes a new trajectory, the local planner updates its internal state and then continues executing the motion, talking to the joint controllers or ROS-I controllers, and handling sensor input depending on the application. Future plans. So we are right now running Foxy Debian releases every 6 weeks. We have already started with the first release. This was a bit bumpy because there were some problems with upstream dependencies, but the version is already tagged. We tested everything, and we hope to get that resolved really soon. In the future, this should be more smoothly, and we try to make to couple this with really frequent strings of Move one as well, so that both versions are always up to date. Then we are planning to switch the main branch to rolling Ridley in Q1 2021, so that we always have the latest versions of ROS enabled, and we want to reduce any time of we want to reduce the maintenance effort switch to new distros and to incorporate any updates in the ecosystem. And this should allow us to make even more frequent releases. For instance, experimental nightly releases with the latest distro versions. Then there is already OS X and Windows support. We are still working on enabling CI for that, and to clean up the last bits and pieces that are still missing for this to work really reliably. For Q3 2021, we are targeting the Galactic release. At this point, we hope to have a lot of applications ready and to have the remaining parts of Move It ready for it to be considered a really usable application for production purposes as well. Also after that, we expect that we will start branching off from Move It 1. So maybe the frequent syncs won't be possible anymore, but we will still continue on cherry picking the bug fixes and features that we still want to share between the versions. The upcoming work for the next weeks and months is to port more of the Move It ecosystem, the Move It task constructor, the Move It calibration package, and other parts that don't strictly belong to the main Move It repository. Then we are working on redesigning the Move It config based on the new Python launch files that we want to use and the changes that the setup assistant is required to have, because many of the features that we want to realize in the future, like dynamic launch files, lifecycle management in the launch files, and the refactoring of the Move It repository based on ROS-II component nodes, is only possible if we have a more flexible approach in the Move It config design. Then there is other plans to pretty much reevaluate where we are standing with the current roadmap. We already have some visions for future milestones, but we want to make a more focused long-term feature roadmap in Q1 2021, where we also engage more of the community and hope of getting everyone on board to switching to ROS-II sometimes the next years, hopefully. And then, of course, we want to push for more hardware integration. It's a chicken and egg problem, pretty much. Everyone was waiting for more hardware support to start working with ROS-II. But at the same time, ROS-II will always stay really early while there's not much hardware support. And that means we try to really push for that in the future, and actually now already. So we are working on a demo with Hello Robot Stretch prototype. This is a mobile base with a manipulator and a sensor that pretty much requires all the bits and pieces of ROS-II to work together nicely. And we are planning to have a nice robot application for that ready the next weeks. Also, we are working on a Universal Robots ROS-II driver, at least an alpha version, that allows us to run all the things that we want to test with Move It 2 on the UR5 or UR5E, and have trajectory execution and position controllers ready for testing Move It server and the usual planning pipeline and trajectory execution features. And then another interesting demo. With eProsima, we're working on integrating an IMU board sensor input for which uses micro-ROS, and show what the performance is when using that as input for motions. On the right, you see the simple integration of using the IMU input as target goal poses, which are moved to using motion planning. But this will be changed to a more real-time pipeline so that we can show how low the latency is between a macro-ROS hardware input and the actual controls that we derive from that. So I hope this wasn't too much at the same time. Please reach out if you have any interesting work you want to do with Move It 2 and get involved. We need every help we can get. Thanks a lot.
Thank you, Henning, for a very impressive presentation. Great to see the progress the Move It team has done in the last couple of years. Also, very great to see that you already have a working demo for the hybrid planning as well. So looking forward to the next updates. So next up is Gilles Chabert, Robotics and Cobotics R&D Engineer at IIT Jules Verne. He'll be presenting ROS-I FTP result trajectory validation using interval computations. So Gilles, if you can hear me, you can switch on your cameras and mic. And
can you see and hear me?
Yes.
Okay, thank you, Ash, for the introduction. So this talk is about a work we have started within the ROS-I project this year, but we imagine to be something like a long-term project. And the goal of this project is to use interval computation inside ROS. So I will share my screen. So you see my screen, right?
Yes.
Okay. So as I've just said, it was this work has been funded so far by the ROS-I project. And first, I will explain you very briefly what interval computations are about. So basically, interval computations is a set of numerical tools that allow to solve equations in a complete and validated way. So to show you to exemplify the idea on a very simple case, consider the equation x squared equal 1. So if you ask this question to a traditional numerical tool, the answer will be something like the solution is close to 1, something like 1, and or minus 1, but you usually only have one of the solution, and you don't know how far you are from the actual root of the equation. So what interval computations do is they give you the two solutions. So this is what we call completeness, and each solution is given under the form of an interval that rigorously enclose the actual solution, the real one. And this is what we call validation. So this example gives you the basic idea of what interval computations can allow to do. There are several tools, of course, that already exist, but I've been developing myself a library called IBEX for now a couple of years. And the two top level application of this library are for system solving, as I've just showed you, but of course you can solve systems of several equations, and global optimization. And some relevant facts, the library is open source, it works on every platform, and it will soon be distributed as a standard Debian package, and we are working hard on it these days. So what is the goal of the project? So it's simply to give the ability to use interval computations inside the ROS framework. So it's more a prospective project compared to the previous presentation we had. But we still have some nice things to show you. And this will give rise to the IBEX ROS package. And a version of the code I show you today is already available on GitHub. But the first official release will be issued in early 2021. So the current code contains several contributions already. So one is for the computation of forward and inverse kinematics of serial manipulators. And the second contribution, the main one so far, is about path planning, and we've developed an algorithm to, as I will show you, to validate trajectories, either with, in the case of rigid bodies displacements, or the serial manipulators. So let's start with the first contribution. So as I show you on this slide, you have a robot and you have a fixed given pose of the effector. So you can see on the 4 pictures that is the same each time, and you want to compute all the possible joint positions to reach this pose. So you have 4 in this case. So what this is the typical things we can do with interval computation. And this is what we have done. And here is the code. So as you can see, is just a few lines. So on the first, I hope you can see my mouse. So the first line, you first define what I call the serial robot object defined in the ROS namespace, and you just feed with standard URGF description. Then you define the target pose you want for the effector. So it's here a 7-size vector. You have the position and the rotation here, and it's an you can even give uncertain pose. In this case, you will calculate all the solutions that are compatible with all the poses that you are inside this vector. But in the example here, I provide only fixed values. And then you simply call IK function on the robot object with the posing argument, target posing argument, and then you get back in return a structure from IBEX. This is a solver structure, and as you can see on the few lines below, it's very simple to iterate over the solution with this data structure. And then if I run this simple program, I obtain the following display. You have the 4 solutions that appear on the screen. And each time, as I explained to you, the solution is a set of joint position. Here you have 6, but I just showed the two first. And each time the joint position is given under the form of an interval. Here the interval is very, very thin because the pose I've given was a single point. But if I would have given an uncertain pose, then I would have obtained more large intervals. So this is the typical kind of thing we can do with intervals. So let's move now to path planning. So we have considered in path planning two objects. One is the moving one, and the other is the fixed one, which can be a full scene. By the way, so it's basically the obstacle. And the algorithm we provide is a local planner. So what it does is given an initial starting pose of the moving objects and a target pose of the moving objects, then it calculates the maximal time of displacement, the maximal displacement you can do with the moving objects to reach the target pose until a collision occurs. So here the trajectory is, as you expect, an interpolation in the set of space isometries. And I can show you a quick demo. So just before a note, to handle the mesh geometry, we devised a clever data structure that is basically a set of recursive set of balls that represent the geometry at different scales, as you can see on the pictures here. And before running the demo, here's the code. Basically, you have a mesh class defined in the ROS namespace. So you declare 2 mesh, one for the fixed object, one for the moving one. You give standard STL file name. Then you define a transform for the fixed object there is a I haven't seen that before, but here it's a typo. It's the fixed object, so you basically settle the fixed object at a given pose. Then you define the start and the end transform for the moving object, and then you just call a local planner with the moving object, the first one, and the start and ending pose, and then you can calculate the maximal time before collision. And the time is between 0 and 1, and if the answer is 1, it means that there is no collision. So I can show you this. So Volga is the temporary name we give to the IBEX ROS project. So you can see here, the object are 2 forks, and what this means is that there is no collision, as you can see, although the moving object is passing through the fixed one. So maybe it was a little bit fast. I can show it again. So you see how the balls are involved in the recursive structure of balls are involved in the computation. So let's get back to the presentation. We did the same with kinematics. So the principle is exactly the same, except that the interpolation is not in the Cartesian space, but in joint space. So we have a starting joint configuration, ending joint configuration, and again, we calculate the maximal time before collision occur in the trajectory that is linear interpolation as expected. And the code is very similar. Just notice that we have replaced the moving object by a serial robot, the same class we used earlier with the inverse kinematic example with the URDF. Then we settled the fixed object. Sorry, there is a typo here, the same way. And we have a starting configuration, ending configuration. Here is just a regular vector. And then we call the planner the same way, except that now we feed it with the robot. Again, the fixed object, the starting and ending configuration. Here you have the link number because you can choose to only consider a specific link. But in the final API, if you don't specify the link, then it will consider all the links. And then you calculate the maximal time. And again, I have a demo to show you. So it's with the UR10, and so here you wait a little. Of course, there are some computation time before it obtained the maximal time, and then you have the object. The fixed object is again the fork, and you can see the balls that are involved in the computation until, and in this case, there is a collision, so we can detect it. So we also made a plugin for Move-it. The idea was to embed our local planner in OMPL. However, I would not recommend its usage because we have realized that embedding interval computations in a stochastic search was prohibitive. So with this, I would not really recommend to use it, but we have tried that. So now I will conclude. Validation computations are now possible under ROS because we made a connection between IBEX and ROS, and there are already several examples of nice things we can do with that. The shortcoming, as I evoked just before, is computation time is not bounded. So you cannot use interval computations in a real-time context. It's only suited for offline usage. So this is the price you have to pay to obtain complete and validated computations. The first release is imminent. There is already a pre-version of the code that is available on GitHub, but the official the first official package will be available in early 2021. And so keep in touch if you're interested. So thank you for your attention.
Thank you, Jill, for an amazing presentation. We have quite a few questions. Some have already been answered in the chat, but if everybody could switch on their cameras, we could have a small panel session and we'll try to answer these questions. Great. Yeah, great. So I think the first one is for you, Jordan and Lopez. We already had some discussion on the chat. So in your presentation, you said that ROS2 control is real-time safe, and you also mentioned hard real-time requirements. How do you ensure hard real-time capabilities without hardware? Does ROS control really guarantee hard real-time or soft one? If so, how?
Okay. Yes, pretty much. I think Geeks. I'm probably gonna butcher your name. Sorry, Mr. Horn. Sorry.
Yeah, please go ahead.
No, I'm talking about. I think his name is Gies van der Horn. That already answered in the chat. Pretty much, I think he nailed it. So when I talk about how ROS2 control ensures real-time safeness, I'm always keeping it in the scope of ROS2 control. So yes, of course, if you want to have a hard real-time system, you still need an operating system that is hard real-time and all the elements that are used by ROS control to be also real-time safe. You can, and unfortunately, you cannot just slap some code into a controller, fit it into ROS control, and hope it to magically work. But what we can do as ROS developers or ROS2 control developers is that make sure that the core code is real-time safe, and so are the controllers that are provided with ROS2 control. So that if you run them in an operating system that, such as Ubuntu RT Preempt, an operating system that gives you real-time capabilities, then you are safe. Then you are safe to go. But again, this is just ROS control. Just would be one piece of the chain. You need to have controllers that are real-time safe, and of course, the hardware abstraction layer or the drivers or whatever is controlling the hardware must be real-time safe too. I hope I answered your question.
Yeah, thanks a lot, Jordan. Henning, the next one is for you. How are the 4 stock values used in the hybrid local planners?
Excellent question. So we have looked into all kinds of hybrid planning approaches, and what we want to achieve with our architecture is to allow to cover the broadest set of applications that you can implement with hybrid planners. So sensor input is just one part of a local planner capability, and we try to just provide an interface that you can implement, and you would basically have a subscriber or some kind of message communication with your sensor, or maybe even your sensor driver directly to use in your local planner. So it will be based on what kind of sensor input you want to use, and if it's a really custom use case, or if it's maybe a generic use case that we will implement as a default. Right now, we are working on 2 demos. One will be purely based on collision checking, so the sensor input will be some changes to the scene, and the collision checker will then notice the changes to the scene. So the local planner will plan with that collision representation that we have. And another will be maybe some visual constraint that we want to solve with a local planner. And in that case, we might switch to a more custom message communication in the local planner. But in the end, this is not really our focus yet. We want to provide that architecture, and we're still figuring out what's the best implementation for what application you want to run.
Thanks a lot for the explanation. Gilles, probably the next one you could take up. How does the IBEX ROS package compare to KDL for computing the IK?
Yes, I've just actually answered on the chat, but I will explain now. So IBEX will calculate all the inverse kinematics. In the case of a serial arm, you have several solutions, and IBEX will enumerate all the solutions, and it will provide them under the form of intervals that guarantee the actual value is inside. So it's a kind of certified answer. So it's exhaustive and certified answer. But the shortcoming, as I said in my presentation, is that you don't actually know how many time it will take. So it may be very fast. In the example I gave on the presentation, it almost answered immediately, but it can take several seconds and several minutes sometimes. It's very difficult to know in advance. So it's only for offline usage. This is really the main restriction of that.
All right, thank you. Next one, probably Jordan and Henning, both of you could take that up. I'm not sure if this was already answered in the chat. What RT tasks required to be on the user's computer for ROS to control and move it to? For example, should the preempt RT patch be adapted, or the packages in ROS to meet the requirements already?
Could you repeat that? I think I didn't really get the question.
What RT tasks required to be on the user's computer for ROS to control and move it? For example, should the preempt RT patch be adapted, or do the packages in ROS to meet the requirements?
You definitely need the RT preempt patch, or at least if you are not going to be working in the RT preempt patch, maybe you can try with a low latency kernel, but you will need to set up at least a CPU isolation. Still, the safe bet to go is with the RT preempt patch. And yes, outside of Ubuntu, I don't think you can make it work in Windows, unfortunately.
Yeah, I think well, with Move It, we haven't really looked into that field too much yet, so there's not a lot that I can talk about right now. But I think for the beginning, what Jordan said is totally right. You would have to stick with Ubuntu and set up your environment that way. There's nothing default that you can run out of the box on other platforms or so.
I mean, by the end of the day, you can have your software can be all the real-time safe you want, but if the operating system doesn't match those requirements, then it's pointless.
Yeah, exactly. This also goes for local planning, by the way. So only because local planning is supposed to run online and hopefully be in real time, it still depends on what you actually solve with a local planner. And if it's a ROS controller that is your local planner, like a trajectory controller or a position controller, then it can be real time. But it won't be real time if you do like complex collision checking in there and your latency rate goes down because of scene changes that are not that manageable.
If I may add, is that real-timeness safety, it's not a requirement for ROS to control or for Move It. It's typically something that you need if you need a very high control frequency, like, I don't know, 500 Hertz or more. But if your hardware is fine with being controlled at 30 or 50 Hertz, probably real-time safety is not required. It's something that you need for higher frequencies, but not a must. And correct me if I'm wrong, but I don't want the people to get the impression that unless you're using a real-time compatible system, you cannot control a robot with ROS to control.
You want real-time if you want to have a smooth trajectories, basically. If you have a real-time loss between a trajectory, you will just see a jump in your motion, usually because you are losing references in the motor. Depends, of course, of the kind of the trajectory. Maybe if you are, instead of you doing points, you are controlling torque or in current, maybe the result is different. But usually that's the reason why we require real time. Maybe in that case, you can make do with soft real time. You don't need hard real time.
Yeah, I would add that real timeness would be a property that you would have for certain planners or certain solvers or certain control interfaces. But it won't be a general property of move it or so. It's really specific to what actually you want to run. And if you have like an online motion planning setup, then you could pick between local planners that are real-time safe and that can be run directly as controllers. But that doesn't mean that this holds true for all kinds of hyperplanners that we will provide.
Last one is for you, Victor and Jordan again. We could take this one last question before we end the session. The current implementation looks quite a bit like ROS control, that is plugins in a single process, as in ROS-I version. Was an architecture where controllers are ROS2 nodes considered. That would make chaining controllers very convenient.
So, sorry, what's the question?
Yeah, did you consider basically an architecture with ROS2 nodes instead of using them as plugins?
Okay, the funny thing is that actually controllers are intended to be ROS lifecycle nodes. So yes, they are nodes. The problem is that we have to move away from that implementation right now because we have some unintended behaviors between the controllers and the controller loader in regards to the resource management. But it's the intention to go back to lifecycle nodes sometime in the future, because I mean it makes a lot of sense, because controllers in the end have the same kind of lifecycle as lifecycle nodes. They can activate it, they can be deactivated, they can be started and stopped, and they are loaded. So it makes a lot of sense, and also it would be cool because this would be easily integrated with the ROS2 command line interfaces, so you can actually check the status of the controllers from a standard tool instead of using custom services inside the controller manager. But right now,
yeah, just one thing that for now all the controllers need to be loaded as plugins inside the same executable. You cannot, I mean, you can have different nodes in the same executable. That's how each control is a node, like Jordan was saying. But you cannot have a controller as an independent node, mainly because for the part of resource management, claiming interfaces and providing interfaces is, I mean, right now it cannot be done across multiple executables, mainly because the real-time safety, you cannot publish references from another node and receive them in the controller manager node in a real-time safe way. We may look into that. I think it's interesting that you could spawn nodes outside of the executable, but it's something that's going to be a lot in the future because it requires major changes. So for now, I mean, we studied, and it's not an option because of the real-time safety, because of how the resource management is done, and there are many reasons for that.
So I think that were the questions we had. So thanks again for all the presentations and also for the discussion. I hope you guys enjoy the rest of the conference. Thanks a lot.
thank you very much.
Yeah. Just one announcement to the audience that you should be able to still, if you haven't already caught the exhibitions from yesterday, you can still go to the exhibition session section of SwapCard, and you can see a couple of live demos. Just one disclaimer is that the ABB demo is not working through SwapCard. So please click on the YouTube link, and then you should be able to see the live demo on their YouTube link. But you should still can ask questions directly in SwapCard or also in YouTube chat. Thanks a lot once again. Bye-bye.